Hey everyone, and welcome to today's Explainer. We're doing something really cool today. We are actually unpacking the chapter on construction from the Grade 9 Kaushal Vikas curriculum. We're going to explore that amazing life cycle of how we take just plain raw materials and turn them into physical reality. I mean, it is literally an incredible journey going from a simple idea in someone's head to a massive standing structure. To really grasp the immense power of building, let's start big, really big. We're talking about one of India's highest structures, the magnificent Tehri Dam in Uttarakhand, standing at a staggering 261 meters tall right across the Bhagirathi River. Wow. It perfectly captures the sheer scale of what human engineering can actually achieve. You see, construction isn't just about throwing together small houses, it's literally about reshaping our entire environment to provide irrigation, electricity, and absolute safety for millions of people. But, okay, before we go building anything, we gotta nail down our core concept. What is it? Well, construction is fundamentally about creating the spaces that protect and serve us every single day. From ancient humans looking for shelter in caves, all the way to our modern multi-story skyscrapers, the goal hasn't actually changed. It's all about enabling us to live safely, work comfortably, and basically shield ourselves from the weather. So here's our blueprint for this explainer. We're going to track the project lifecycle through 6 main steps: the basics of building, planning and blueprints, materials and tools, the math of construction, brick by brick, and finally, finishing and safety. All right, moving right into Section 1. The basics of building, from foundations to roofs. Let's break down the actual anatomy of a building. Think about the room you're sitting in right now. That structure relies on 6 basic elements to stay standing. It all starts at the bottom with the foundation. That's what safely transfers all the weight into the ground and actually protects against earthquakes. Then you've got walls for enclosure, horizontal beams to carry the weight of the floors above, and vertical columns holding up those beams. Cap it off with a roof, pop in some windows and doors for light and air, and boom. But here's the catch. If even one of these elements fails, the whole system is totally compromised. Now, there are 2 main ways buildings actually support all that crazy weight. First, you have simple load-bearing walls. This is basically where the walls themselves do all the heavy lifting, carrying the roof's weight straight down to the ground. It's super cost-effective, perfect for a single-story home. But then on the other side, you have RCC. That's reinforced cement concrete construction. This is where concrete gets reinforced with steel bars to build this massive skeleton of beams and columns. This is exactly what you need to support huge skyscrapers and make structures earthquake-resistant. On to Section 2, planning and blueprints, defining the scope. Because look, before you mix a single drop of water into your cement, you have to do the invisible work. You gotta plan. Setting up your project scope comes down to 4 really critical steps, because you can't just go out and start digging a hole. First up, you have to define exactly what you're building. Are we talking about a boundary wall, a ramp, maybe a shed? Second, you check your resources. Do you actually have the bricks, the sand, and the people to do the work? Third, you gotta ask, is this even useful to the community? And fourth, where is this happening? You have to consider space, safety, and site access to make sure the whole thing is actually viable. Once you've got that figured out, you translate that idea into technical drawings. A lot of times this means using CAD, computer-aided design software. These drawings are essentially the language communicating the exact scale and dimensions from the designer's brain straight to the builders on the ground. It's what makes sure that 1 centimeter on the paper perfectly translates to, say, 100 centimeters out in the field. Trust me, getting this right prevents incredibly costly mistakes and wasted materials later on. All right, Section 3, materials and tools, gathering the right resources. And what's really fascinating here is how just picking the right materials acts as the true foundation for everything that follows. Okay, here's a major distinction you absolutely need to know. A lot of people mix up mortar and concrete, but they do totally different jobs. Mortar is basically your glue. It's what you use to stick bricks together or lay down tiles. But concrete is the heavy lifter. You mix cement, sand, water, and gravel, and that concrete actually forms the load-bearing structure itself, like your massive foundations or ramps. Of course, alongside the materials, you need the right tools, like a trowel for spreading your cement and a hoe for mixing it all up. But hey, you absolutely must prioritize safety gear. Think about the heavy rubber gloves you need to wear while handling wet cement. Construction materials can be super harsh on your skin, so taking really simple safety precautions prevents awful injuries and just keeps the whole project moving smoothly. Let's move to Section 4, the math of construction, estimation, and calculating capacity. We're going to dive into the math right now to figure out exactly how much material we actually need. This is where engineering directly meets economics. I absolutely love this perspective from the curriculum chapter. Think of a building's volume as its physical capacity to literally contain bricks. You see, you aren't just building a flat wall, you're filling up a 3D space. So by calculating the total volume of your planned structure and then dividing it by the volume of just one single brick, you can figure out exactly how many bricks you need to buy. It's brilliant. But wait, here is a massive pro tip straight from the source text. Engineers will calculate that total number of bricks, and then they always add 10% to it. Why? Well, because the real world is messy. Bricks break on the truck, or you have to cut them to fit weird corners. Adding that 10% buffer means you aren't going to have to stop construction just because a few bricks got chipped. So the crucial thing is organizing all of this math into what we call a bill of materials. Just like a professional team would do for any building project, you list every single item, the quantity, and the estimated cost. 1,200 bricks, 50 kilos of cement, sand, the cost of labor. This single document is really the financial heartbeat of your project. It's the only way you ensure you're staying completely on budget. All right, section 5, brick by brick, the physical build. Our planning is done, the blueprints are drawn, materials are here, math is checked off. We finally hit the climax, the actual physical act of building. This is the process in beautiful action. Following the exact layout lines marked on the ground, the builders actively put the structure together. They're mixing the cement, they're carefully laying down pre-soaked bricks, and they're spreading that mortar with a trowel. This is exactly where precision really matters. You have to ensure every single layer is perfectly aligned so that gravity is working with your structure, not against it. And hey, speaking of that mortar, here's another insider rule of thumb from the chapter about the mix ratio. To make standard or really strong mortar for bricks, you typically go with a ratio of 1 part cement to 4 parts sand. Basically, for every 100 standard bricks you lay down, you're going to need roughly 5 to 10 kilograms of cement. If you get this mixed wrong, you can severely weaken the entire wall. No pressure, right? Now, here is a step so many beginners completely forget: curing. Just because the structure is built doesn't mean you're done. You literally have to grab a watering can or a hose because curing is this absolutely vital process where the new structure has to be kept wet. See, concrete and mortar don't just dry out to get hard. Actually, scratch that. They undergo a chemical reaction that needs moisture. Keeping it wet is what allows it to harden up and reach its maximum stone-like strength over time. Section 6, finishing and safety. The final touches and lasting impact. We are finally in the home stretch here, focusing on the longevity of our project. Because look, a building isn't finished just because the bricks are laid. You've got essential finishing works. Plastering gives you that nice, smooth surface. And painting? Well, painting does way more than just make it look pretty. It's actually a critical defense mechanism. It prevents water leakages, keeps pests out, and drastically increases the overall lifespan of the whole construction. So, as we wrap up this explainer on the construction chapter, I want to leave you with a really provocative thought straight from the text's exercises. Imagine a builder decides to just skip using a simple alignment tool, like a plumb bob, and just eyeballs it to see if a wall is straight. What's the real technical risk there? Well, if that wall is even slightly out of plumb, meaning it's not perfectly vertical, how might gravity silently exploit that tiny little error over the years? Could it eventually compromise the entire building's safety? It just goes to show you, in construction, every single millimeter literally counts.